For centuries, the formidable English Channel stood as a natural barrier, shaping histories and destinies. But for just as long, visionaries have dreamed of bridging this divide, of connecting Britain to continental Europe not by sea, but beneath it. It was a dream of unimaginable scale and complexity, one that would push the very boundaries of engineering and human endurance. This is the story of the Channel Tunnel, a project that defied skeptics and transformed a seemingly impossible vision into a 31-mile, subterranean reality. The world's longest undersea tunnel, a true testament to ambition. The concept of a fixed link beneath the channel dates back to 1802, when French engineer Albert Mathieu Fadier proposed a tunnel for horse-drawn carriages, complete with artificial islands for ventilation. Over the decades, numerous proposals followed, each more audacious than the last, reflecting the evolving technological capabilities of the era. From early Victorian attempts to 20th-century studies, the dream persisted, often halted by political tensions, financial crises, or the sheer technical impossibility of the time. The challenge was always immense, but the desire for direct connection remained. By the late 20th century, a confluence of political will and technological advancement finally set the stage for the Channel Tunnel's realization. After decades of renewed studies and stalled starts, the governments of the UK and France signed the Treaty of Canterbury in 1986, committing to the project. This was not merely a construction endeavor, it was a complex international agreement, privatized to minimize taxpayer risk. The vision was clear: 2 main rail tunnels for high-speed trains, flanked by a smaller service tunnel, all burrowing deep beneath the seafloor, connecting 2 nations like never before. The scale of the undertaking was staggering. Constructing a 31-mile tunnel, with 23 miles of it submerged beneath the notoriously turbulent English Channel, presented unprecedented engineering challenges. The primary concerns were geological stability, immense water pressure, and the logistical nightmare of excavating and removing millions of tons of spoil. Engineers had to contend with the potential for water ingress, the precise alignment of tunnels meeting in the middle, and ensuring the safety of thousands of workers in an unforgiving environment. It was an undertaking that would test human ingenuity to its limits. From day one, the Channel Tunnel was destined to be a 31-mile engineering marvel. This wasn't just about digging, it was about creating a resilient, permanent link that could withstand the immense pressures of the sea and serve as a vital artery for decades. The project demanded innovations in every field, from geological surveying to bespoke machinery. Every decision, from the choice of tunnel lining to the ventilation systems, had to be meticulously planned and executed with extreme precision. It was an endeavor that would redefine the capabilities of civil engineering on an international stage, pushing boundaries like never before. Crucial to the tunnel's success was understanding the geology of the Channel seabed. Extensive seismic surveys and boreholes revealed a consistent layer of impermeable chalk marl beneath the seabed, stretching across the entire 31-mile route. This geological luck was paramount. Chalk marl, while soft enough to excavate, was strong enough to support the tunnel and largely prevented water from seeping through. Targeting this specific stratum allowed engineers to avoid more porous layers of rock and minimize the risk of seawater ingress, significantly simplifying the tunneling process compared to other undersea projects. The true heroes of the Channel Tunnel's construction were the tunnel boring machines, or TBMs. A total of 11 TBMs, 6 from the British side and 5 from the French, were custom-built for this colossal task. These magnificent machines, each weighing thousands of tons and the length of several football fields, were essentially mobile factories. They excavated rock, simultaneously removing spoil and installing the precast concrete tunnel linings. Designed to withstand extreme pressure and cut through the chalk marl with incredible efficiency, they were at the forefront of tunneling technology. The construction strategy involved tunneling simultaneously from both the British and French coasts. This dual approach significantly accelerated the project timeline and reduced the overall construction period. From England, excavation began near Folkestone in Kent, while on the French side, operations commenced near Coquelles in Pas-de-Calais. Each country's TBMs worked independently, yet towards a common goal, meeting precisely beneath the English Channel. This required unprecedented levels of coordination and navigation accuracy, turning two separate teams into a single, unified force against the earth and sea. Meeting in the middle, 23 miles beneath the sea, was a monumental navigational challenge. Engineers utilized a sophisticated laser guidance system, integrating GPS technology, to ensure the TBMs stayed on their predetermined course. Despite the immense pressures, vibrations, and constant movement, the accuracy was astounding. When the service tunnels from both sides finally broke through on December 1, 1990, the alignment was off by a mere 35.8 centimeters horizontally and 5.8 centimeters vertically. This remarkable precision stands as a testament to the skill and ingenuity of the engineers and the advanced technology employed. Between the two main rail tunnels lies a smaller, central service tunnel, a critical component of the entire system. This wasn't merely a safety feature, it was an integral part of the construction process. The service tunnel was always excavated first, acting as a pilot bore. It allowed geologists to confirm the ground conditions ahead of the main TBMs, giving precious time to adapt machinery or techniques if unexpected obstacles arose. During operation, it provides access for maintenance, ventilation, and, crucially, serves as an emergency escape route, connected to the main tunnels by cross passages every 375 meters. Despite careful geological surveys, working beneath an active seabed posed constant threats. Water ingress, though minimized by the chalk marl, was always a concern. Engineers devised robust waterproofing strategies and utilized powerful pumps to manage any water that did penetrate. The sheer pressure of the overlying sea and rock demanded extremely strong tunnel linings. Each precast concrete segment, some weighing several tons, had to be precisely fitted and sealed to create a watertight and structurally sound tube. Safety protocols were rigorous, making it one of the safest construction sites of its time despite the inherent dangers. The Channel Tunnel was an audacious undertaking not just in engineering, but in finance. The total cost of construction soared to an estimated $15 billion, a figure that, when adjusted for inflation, represents one of the most expensive infrastructure projects in history. This colossal sum covered everything: the manufacturing of the advanced TBMs, millions of tons of steel and concrete for linings, extensive geological surveys, labor for thousands of workers, complex safety systems, and the vast logistical network required to sustain operations 24/7. Unexpected geological conditions and financial challenges contributed to cost overruns, but the strategic importance justified the immense investment. A critical, yet often overlooked, challenge was the management of the excavated material, or spoil. The 31-mile excavation generated approximately 13 million cubic meters of spoil. On the French side, the spoil was mixed with water to form a slurry and then pumped inland to a vast quarry, which was later landscaped. The British approach was different. The chalk marl spoil was used to create a 90-acre artificial peninsula known as Samphire Hoe, reclaimed from the sea near Dover. This man-made land is now a thriving nature reserve, a unique ecological legacy born from an engineering feat. After years of relentless digging, the ultimate moment of triumph arrived. On December 1, 1990, a British tunneler, Graham Fagg, and his French counterpart, Philippe Cosette, ceremonially shook hands through a small pilot hole in the service tunnel. This emotional breakthrough, broadcast globally, marked the physical connection of Britain and France beneath the waves. It was a powerful symbol of international cooperation and engineering triumph, signaling that the most challenging phase of the 31-mile journey was complete. The sheer joy and relief were palpable, celebrated by workers, engineers, and nations alike. With the service tunnel connected, work continued on the two main rail tunnels. The TBMs from each side were either dismantled underground or driven into vast caverns and buried. The final stretches of track were laid, sophisticated signaling and power systems installed, and ventilation, cooling, and fire suppression infrastructure finalized. On May 6, 1994, after nearly 7 years of intensive construction, the Channel Tunnel was officially inaugurated by Queen Elizabeth II and French President François Mitterrand. The dream of centuries had become a reality, ready to serve millions. The impact of the Channel Tunnel on European connectivity was immediate and profound. For the first time, passengers could travel directly between London and Paris or Brussels by high-speed train, bypassing the traditional ferry or air travel. The Eurostar service revolutionized cross-channel journeys, dramatically reducing travel times and increasing convenience. What once took hours of sea travel, often subject to weather delays, became a smooth, swift passage. It didn't just connect two countries, it integrated them more deeply into a unified European rail network, transforming how millions experience continental travel. Beyond passenger travel, the Channel Tunnel significantly boosted trade and economic integration. Freight trains carrying goods, and the innovative Le Shuttle service for vehicles, created a vital logistical link. Businesses could now move products faster and more reliably between the UK and mainland Europe, fostering economic growth and reducing reliance on sea and air cargo. The tunnel became a critical artery for commerce, impacting supply chains and opening new markets. Its economic value, though difficult to quantify precisely, far exceeds the initial $15 billion investment through its continuous contribution to cross-border trade and tourism. The Channel Tunnel stands as a powerful symbol of cooperation, demonstrating what can be achieved when nations unite for a common goal. It broke down a physical barrier that had defined Anglo-European relations for centuries, creating a tangible link that has fostered cultural exchange and deeper understanding. Despite political shifts and challenges, the tunnel remains a testament to the enduring vision of connectivity. It reminds us that even the most formidable geographical divides can be overcome with audacious planning, relentless engineering, and a shared commitment to progress, literally bridging borders. The Channel Tunnel, the world's longest undersea tunnel and a 31-mile engineering marvel, is more than just concrete and steel. It is a monument to human ingenuity, perseverance, and the courage to tackle seemingly impossible challenges. From the early dreams of connectivity to the meticulous planning, the innovative TBMs, the $15 billion cost, and the ultimate breakthrough beneath the waves, every step was a battle won. It stands as a beacon for future megaprojects, proving that with enough vision and collaborative effort, humanity can overcome any obstacle, forever changing our world.